This is Vishal Singhal from Shellstrat. Today we have Mr. Shreyas SK. He's a deep learning researcher at Shellstrat AI Lab. He's taking us through this important topic of sarcasm detection in news articles. This session is being recorded, so it will be posted on our Shellstrat YouTube channel in 2-3 days' time. Uh, and I suggest you keep sending your questions as they come to your mind. Uh, and you can get answers from him in real time. He's an expert in this area, and uh, look forward to uh, have a great session from him. So Shreyas, I am transferring the controls to you.
Okay, I will share my webcam.
Go ahead.
Okay, shall I start the presentation right now?
Yeah, please go ahead.
Yeah, okay. So, hi all, my name is Shreyas. I'm working as a machine learning engineer in HCL Technologies. So, I'm also a part of Cellstat as a deep learning engineer. So, today my webinar topic is on sarcasm detection in news articles. So after this presentation, I will also be giving a code demo. So the code demo, I will be showing the way the natural language processing has been progressed from bag of words, TF-IDF, as well as the static word embeddings like glove. And moving on further, even I will be showing the code demo on FLAIR API by using the stacked embeddings of Elmo and BERT. So let me start with what is meant by sarcasm. So sarcasm refers to the words that mean the opposite of what you really want to say. So the main intention of sarcasm is maybe to hurt someone, or also it might be a joke. So why is it important to detect sarcasm? So the use case of sarcasm detection is mainly in Twitter. So in Twitter, many of them will be posting tweets which will be criticizing the government policies by using sarcastic tweets. So many of the times, these sarcastic tweets will also tarnish the reputation of a company or a person. So in order to avoid all these things, even as well as to avoid the spreading of political hatred amongst the people, it is important to detect this sarcasm in Twitter and also to block it. So the way the natural language processing has progressed, initially we wanted to represent each and every word as a number so that the computer can understand. So the first progression in this way is one-hot encoding. So what is one-hot encoding? So each and every word is represented in a higher dimensional space, and each and every word is converted into a vector of n dimensions. So suppose there are 10,000 words in your vocabulary. So you want to represent each and every word as a new dimension in the vocabulary space. So suppose Rome, Paris, Italy, and France, all these are words in your vocabulary. So when you represent this word as a as a vector, so the dimension of this vector will be of the order 10,000. So out of 10,000 values, only one value will be represented as 1, which will be representing the word Rome, and the rest of all other vector numbers will be represented as 0. So the vectors that we create by using one-hot encoding are very sparse. So as I have mentioned over here, one-hot encoding will create a sparse vector, and the feature space will blow up very quickly. And also the problem with one-hot encoding is it requires very less computational power to convert text data into one-hot encoding. But when you create 10,000 ordered dimensional vectors, it will be the model when the model takes these vectors, it will be very difficult for the model to process and give results. So the one-hot encoding suffers from curse of dimensionality because each and every word is represented as a new dimension in the corpus. And moreover, the main important thing is in one hot encoding, it will not catch the semantics of the words. That means what is the relation between two words cannot be captured by one hot encoding, because each and every word is represented as a number which is 1, and rest of all the numbers are 0 in the vector. You will not get the similarity between two words. So what are the metrics that you use to calculate the similarity between two words? Suppose cosine similarity or Euclidean distance. So when you use these kind of metrics to calculate the similarity between two words, and when you use one hot encoding as a vector, you will be getting the same value irrespective of what the word is. So it doesn't see the similarity among the words, as it treats every word as a new feature. So as I talked in the previous slide, Euclidean distance and the cosine similarity are used as the metrics to calculate the similarity between the words. So in the higher dimensional space, these are not the good metrics to calculate because both of these metrics will suffer from the curse of dimensionality. As I discussed in the previous slide, each and every word is projected as a new dimension. Therefore, the feature space is getting blown up. That's why these metrics are not suitable for calculating the similarity between the words. So the next progression was the statistical methods such as bag of words and TF-IDF. So in bag of words, what we are going to do is initially we'll create a vocabulary of words. So each and every word in the vocabulary will be unique to itself. So suppose there are 10,000 words in our vocabulary, each and every word in the vocabulary will be unique. So for every sentence in our document, we will be calculating what is the frequency of the occurrence of each and every word. Suppose these three are the sentences in our document. The cat sat in the hat, and the cat with the hat. So here, when you consider all these three sentences and find out the unique words in all these three sentences, these are the unique words in these three sentences. So after this, after creating the unique words, you will be calculating the frequency of each of these words. Suppose the cat sat. So here the word the is repeated one time, cat is repeated one time, and sat is repeated one time. Similarly, in this sentence, the word the appears two times and the rest of the words will appear one time. Similarly, in the third sentence also. So even in this diagram, you can see the raw text and the bag of words vector. So these are the methods to convert words into vectors. So after converting the words into vectors, we'll be using machine learning algorithms such as a Gaussian naive Bayes in order to deal with the downstream task that we are dealing with. Suppose if you want to, suppose if the use case is to detect whether the email is spam or not spam. So by using the bag of words vector, we will be calculating we'll be sending these a bag of words vector into the Gaussian naive Bayes, and the Gaussian naive Bayes will be able to classify whether the particular email is spam or not. So the main problem with the bag of words is here we lose the context of the words used in the sentence, because here only the frequency of the words are taken into account, but the language or the sentiment of the language is getting missed. So here we are only knowing what words appear in the document, but it is also important to know where they have occurred to extract the semantics. So here the context as well as the semantics of each and every word is getting missed, because this is a statistical method. This can't consider the sentiment of the language. So the next method is TF-IDF. So the next method is TF-IDF, which is a term frequency and inverse document frequency. So the progression of TF-IDF with respect to bag of words is, in bag of words, we will only count the number of times each and every word appears in the document. But in TF-IDF, what the extra thing that we do here is we will also calculate the frequencies. So what kind of frequencies are we calculating here? So we are calculating the frequency of each and every word that appears in the document with respect to all other words in the document. So by calculating the frequency, what extra thing are we going to know? So by calculating the frequency, here we can find out whether a particular word is a rare word or most frequently occurring word. So we need to differentiate between the rarely occurring words and the frequently occurring words. So term frequency will represent the bag of words concept, and this term frequency is being multiplied with inverse document frequency. Suppose there are 10 documents, and there is a very unique word which is which can be found out only in one document. Then what is the value of IDF? So total number of documents is 10 divided by number of documents with the term T in it. Suppose there is only one document in which the rare word is present. Therefore, what does this division will lead to? 10 divided by 1, and log of 10 is 1. Therefore, you are multiplying 1 with the term frequency. Suppose there is another word which is most frequently occurring word. So these stop words like the, are, is, all these are stop words. So these words are you can find these words occurring very frequently in most of the documents. So the IDF for these stop words will be 0, because the total number of documents will be 10 divided by number of documents with the term T in it. This also will be 10 because it is the most frequently occurring word. Therefore, a log of 1 will be 0, and you are multiplying 0 with the term frequency. So the IDF is the weighting term. You will measure how much information a particular word provides across all the documents, and you will weight it with respect to the term frequency. So the bag of words as well as TF-IDF both are statistical methods. Here we are only counting the number of times a particular word repeats as well as its frequency along the entire corpus. But here the semantics or the context is getting missed. This is the disadvantage by using these statistical methods. So the next progression with respect to the statistical models is word to vec. Here word to vec is not a statistical model. Here we are representing each and every word in a as a word representation without considering the frequencies or the counts and all. So word to vec has two models, which is a SIBO model and a skipgram model. So in SIBO model, what we do is this is similar to fill in the blank. So the target is the blank, and we are giving the inputs as the surrounding words to the blank. So by giving the surrounding words, we are predicting the target word, that is the word that fits in the fill in the blank. So similar to this skipgram model is opposite to the SIBO model. So here we are giving the target word as the input, and we are predicting the most probable surrounding words to that particular input. So the problem with word to vec is here we are taking the local context, but the global context is getting missed, because suppose in NLP you'll be dealing with the data sets which are having millions and billions of words. But when you are dealing with word to vec, when you are considering a particular sentence, and you are trying to predict the target word, or you are predicting the surrounding text with respect to the target word, these predictions are made only with respect to the local context. So the model will be considering only the local information, but the global information is getting missed. But the word to vec method is a transition from using the statistical methods to the vectors for word representation. So here instead of using the frequency and the count, we are using the vectors in a higher dimensional space in order to give a word representation. Here you can see semantics learned for a particular word is only affected by the surrounding words. So the next progression in NLP after word to vec was global vectors for word representation. So in global vectors for word representation, the thing that was lacking in word to vec was we were not considering the global semantics. So in GLOW, we are considering both local as well as global semantics. So we can derive the semantic relationships between words from the co-occurrence matrix. So glove word representations, we can get glove word representations in 50 dimensions, 100 dimensions, 200 dimensions, and also 300 dimensions. So I will be discussing how the model glove is built. Suppose there are suppose there are 10,000 words in the vocabulary. So for each and every word, we will be building a co-occurrence matrix. So what is this co-occurrence matrix? So this tells how many times a particular word is being seen with the another word. So here the word cat is seen with the one time. Similarly, the word on is seen with the one time, and mat is also seen with the word the one time. So we'll be filling this co-occurrence matrix for all the words in our corpus. And suppose I'm talking about a glove for 50 dimensions. So each and every word in the vocabulary is being represented as a 50 dimensional vector. So what is the best way to train this model? So the embedding matrix for glove is trained instead of using random vectors, random vector initialization. We are using the co-occurrence matrix probabilities as the initialization to the embedding matrix. So from the co-occurrence matrix probabilities, we are training each and every word in order to obtain the final global vector. So suppose these are the words. Suppose the word is solid, gas, water, and fashion. So what is the probability of seeing the word solid with ice? So it will be more when compared to the probability of seeing the word gas with ice. Since ice and ice is a solid, you will be having more probability of seeing a solid and ice together when compared to gas with ice or fashion with ice. So here you can see the probabilities order 10 power minus 4. Here it is still less. So we are converting the probabilities into ratios. Here you can see what is the probability of seeing the word solid with ice divided by probability of seeing the word solid with steam. So the word solid and steam can be found very rarely. Therefore, the denominator will be a lesser value. So the whole ratio will be a higher value. Similarly, the word fashion is not related to either ice nor steam. Therefore, the value will be closer to 1. If it is not related to any of the word, then the value will be closer to 1. If it is related to any word, then the value will blow up. If it is not related, then the value will go down less than 0. So the important observation that we can make here is solid and ice are closer together. That means the distance is very less. So we can say ice and solid are similar to each other. So here steam and solid are very far with respect to each other. Therefore, we can say the probability of occurring solid and steam is less. So here we can observe one thing, that is the distance between two words will increase when the probability of a particular word with respect to the another word occurring together is less. So it is inversely proportional. Even here you can see fashion is not either related to ice nor steam. That's why the distance with respect to ice and steam and fashion is very more. And water is equally related to ice as well as steam. That's why it is equidistant with respect to ice as well as steam. So I'll also be showing the TSNE plots for the words in the corpus that I have used for sarcasm detection. So the TSNE plots, these are visualization techniques similar to PCA. So PCA method was introduced in 1934, but TSNE is a very new technique that was introduced in 2008. Using TSNE, what we are dealing with the probability distributions of each and every word in order to represent them in a lower dimensional space. Suppose we want suppose this since this is a 2 dimensions, we will take higher dimensional space as a 2D, and this is 1 dimension. Therefore, lower dimensional space as a 1D. So our goal here is to project the 2D vectors as a 1D vector. So how do we do this? Initially, we'll construct the probability distributions for each and every point. So here we can see in the 2D space, there are three clusters formed over here for blue, red, and green. So for each and every cluster, we'll be forming the probability distributions, and we'll also calculate the PJI. This is a conditional probability. So what is PJI? What is the probability of what is the probability of occurrence of the point J with respect to I? So by calculating the PJI for each and every point, we'll be constructing the probability distribution. So once we construct the probability distribution in a higher dimensional space, we'll do the similar thing even in the lower dimensional space. So in the lower dimensional space, initially we'll initialize all these 9 points randomly. So our goal here is to arrange all these points in this format so that we can replicate whatever we have represented in the higher dimensional space into the lower dimensional space. So when you do the random initialization, for each and every point, you will again calculate the probability distributions. So QJI. So PJI is a conditional probability in higher dimensional space. QJI is a conditional probability in lower dimensional space. Suppose this probability distribution is in higher dimensional space. When you do random initialization in 1D, you will be getting a probability distribution like this. So our cost function is KL divergence. So what does this KL divergence mean? When the probability distributions, when we are comparing two different probability distributions, if they are very similar to each other, then the KL divergence will be 0. When they are dissimilar, the KL divergence value will increase. So initially, because of the random initialization, you can see the KL divergence is more. So the cost function is calculated by using this formula. So as we progress, the cost function will reduce and the KL divergence will also reduce. When KL divergence reduces, the distributions, both of these distributions will become approximately similar. So our target is reached. So this is a background in which TSNE works in order to give us visualizations of each and every word. So coming to FLAIR embeddings, as I discussed before, it was glove. Glove is a static word embedding. That means irrespective of the context in which a word is being spoken, you'll be getting the same word embedding. But in contextual string embeddings, the meaning and as well as the context of each and every word is taken care of. Suppose here you can see these two are sentences: reading a book, please book a train ticket. So in this, the word book in the first sentence is a noun, and the word book in the second sentence is a verb. So based on the context, the meaning of the book is changing in these two sentences. When you use the static word embeddings like glove, you will be getting the same word embedding for the word book in the sentence 1 as well as in the sentence 2. But this should not be the case. So while you use contextualized string embeddings, you will be getting different word embeddings for the word book in first sentence as well as in the second sentence based on the context. So how this is being done is each and every word is trained as characters. So here in this figure you can see George Washington was born. So each and every word is fed into the forward as well as the backward LSTM in order to get the word input word representation for the word George. So for every word, you are dealing with the character level embeddings. So once you get the character level embeddings, you are dealing with the downstream task. Suppose it might be a sentiment classification problem, or as it is represented over here, it is a NER. So the embeddings are contextualized by surrounding text. Same word can have different embeddings depending on the context. So in the code demo, I will be showing you the stacked embeddings performance. I have used FLAIR API, which is available in Python. So there is no need of downloading the word embeddings file for each and every dimension, because suppose in internet the glove representations are available, 50 dimensions, 100 dimensions, 200 dimensions, and 300 dimensions. So the 300 dimensions glove word embedding file is about 700 to 800 MB. So there is no need of downloading each and every embedding in order to train your model. FLAIR embeddings will provide already inbuilt embedding vectors. Okay. So this was a performance that I have observed by using glove embeddings. So here you can see the accuracy, training accuracy was 83%, testing accuracy was 80%. This was a training and testing loss. So without using the glove embeddings, the model is overfitting, and even the performance is very poor. Just after the first epoch, I am getting around 83 to 80%. So what is the performance with by considering the glove embeddings? So here you can see the model has converged well when compared to without glove embeddings. So here the training accuracy is 88% and the testing accuracy is 80%. Here I have used 200 dimensions glove vectors. So the next one is performance with the stacked embeddings. So I have used a FLAIR API and I have stacked a BERT as well as ELMO embeddings. So after doing this, the training accuracy is 89% and the validation accuracy is 86%. So when I consider the context, I am getting a higher validation accuracy when compared to not considering the context. So this is a comparison that I have made amongst the models: bag of words, TF-IDF, glove, BERT, and ELMO. So when I used bag of words, the accuracy for the testing set I was getting is 72%. When I used TF-IDF and Gaussian Naive, the testing accuracy was 66%. Glove embeddings, I am getting 80% validation accuracy, and by using the stacked embeddings with BERT and ELMO, I am getting 86% validation accuracy. So I have used all these methods in the way the natural language processing has progressed from initial days, by using the statistical methods and as well as the static word embeddings and contextualized word embeddings. So now I'll be showing you the code demo. Okay. Okay, so the sarcasm detection problem that I am dealing in this webinar is a supervised learning problem. So here the input data set, what I am getting is, I am getting, this is from the news articles. There are two separate news articles, Huffington Post and as well as another one. So from these two news articles, Onion and Huffington Post. So this data set is built by using the sarcasm that is reported in these two different news articles. So the data set I'm having is included with the headlines of each of these news articles and the classification whether that particular headline is sarcastic or not. And this is the article link. So in order to build this bag of words or TF-IDF statistical models, I have done some pre-processing. I have removed punctuations and have lowered all the text and removed the stop words, because it doesn't matter even if we remove the stop words for statistical methods, because they are not anyways considering the semantics. So after this pre-processing, okay, let me change the theme. Okay, this plot shows the frequency of each and every word in the corpus. So these are the most frequently occurring words which are which are classified as sarcastic, and these are the most frequently occurring words which are classified as not sarcastic. And I have made bigram plots also for sarcastic and not sarcastic words. So these are the most frequent words. These are the most frequent bigram words. From these plots, anyways, you can't infer anything, because sarcasm means you are actually referring to the opposite meaning of what you really want to convey. So just by seeing these unigram or bigram frequency plots, you can't infer anything. So as I said to you while I was giving the presentation, this is a PCA representation for word embedding. So here you can see all the words are very close to each other, and you can't make out the similarity between the words. But here you can see the distinction: woman, child, and man have been placed together. But here you can't find out the difference. That's why we'll be using the new technique called TSNE. So when I used the TSNE plot, here you can see the KL divergence after 250 iterations is 69, and after 1000 iterations it has got reduced to 0.48. So here you can see how each and every word is represented very far from each other by giving you a clear picture. So here you can see report and study are together, find, make, get are together. Here also man, woman, and child are together, day and year are together. So based on the similarity between the words, these are represented in a TSNE plot. And American and Trump are also closer together. So when I use the bag of words model in order to convert the words into vectors, uh, and I used a Gaussian naive Bayes. So this is the accuracy on the testing set, which is 72%. So here bag of words is done for unigram. So the next one I had done for bigram. Yeah, here you can see the n-gram range 1, 2. So here the accuracy on the test set was 70%. So when going to the next statistical model, that is TF-IDF, and using Gaussian naive Bayes, the accuracy on the test set is just 66%. So here, by seeing all these things, we can say that the statistical models will anyways fail to consider the semantics as well as the context in the language that is being used, because in sarcasm it is very difficult to predict sarcasm, because here the entire sentence has to be read based on the context and as well as the semantics, because it is meaning the opposite of what it is being said. So even the punctuations as well as stop words will play an important role in detecting the sarcasm. So moving on to glove embeddings. So moving on to glove embeddings after doing all these pre-processing stuff. Yeah, I have used maximum length as a 51, maximum length of each sentence, and 10,000 features. Embedding size is 200 I have used actually. And I have built an LSTM model, bidirectional LSTM, because here it is important to consider the context in the forward as well as in the backward direction. So this is the model architecture. So when I used a 100-dimensional word embedding, these are the number of parameters. So there are 128 units in the LSTM. Since this is bidirectional, there are 128 into 2, which is 256 units. And further, this is the dense layer, 40 units and 20 units in these two dense layers. And binary cross entropy is a loss function, and Adam optimizer is used. So just for 10 epochs, we can see here the accuracy for the training set is 98%, and for the validation it is 78%. So this is a performance observed without using the glove vectors, without using the embedding glove embeddings. So what is the enhancement that we can observe after using the glove embeddings is, okay, uh, in the older versions, TensorFlow 1, this was the LSTM was represented as a CUDNN because these bidirectional LSTMs were being run on GPUs. This CUDNN, it is faster than a normal LSTM, approximately 15 times, and it is 54 times faster over CPU. So because LSTM takes long time during training the model, this becomes important during the deployment of the model. But what happened in TensorFlow 2.0 is this CUDNN was removed, and it was just represented as LSTM. But still, this LSTM in TensorFlow 2.0 runs on the GPU. So there is no need to import CUDNN, and it is anyways removed in TensorFlow 2.0. So here what I have done is I have downloaded a 200 dimensional glove embedding from the internet. It is around 600 MB file. So by using this glove embedding, I have trained the bidirectional LSTM. So here you can see only the LSTM. In TensorFlow 1.0, if you are using, you need to represent this as CUDNN LSTM. So by using the glove embeddings, the accuracy that I'm getting is 95% in training and 80% in testing. So without using the word embeddings, the model was overfitting. So by using the glove embeddings, the model has at least narrowed the gap between the training and the validation sets. So as you can see, whenever the loss is loss of the validation set is increasing, we'll take that particular epoch as optimized one, and the accuracy corresponding to that epoch is being reported here. So going with the FLAIR embeddings, so here I did not do much pre-processing because FLAIR embeddings, they are contextual, and in order to detect sarcasm, it is very important to consider even the stop words. That's why I did not remove the stop words, and I did not lematize. So here you can see the FLAIR API has been imported, and I have used a PyTorch for this. So these are the list of embeddings that can be extracted from FLAIR API. Character level stacked embeddings, FLAIR, BERT, Elmo, FLAIR is repeated again. Yeah. So in FLAIR embeddings, we have two separate ones, which is a FLAIR forward and FLAIR backward. So the FLAIR forward is a forward LSTM, and FLAIR backward is a backward LSTM. So you can use a stacked embeddings and stack both of these forward as well as backward LSTMs, so that you can get a better accuracy. So here I have used the stacked embeddings, and I have stacked BERT as well as Elmo. So you can see, since I've used PyTorch, each and every word in our corpus will be converted into tensors of a particular dimension, whichever we choose. So here, each and every word in our corpus is converted into CUDA representations in GPU, and you can see for each and every token in the sentence, we are storing W and S as a variable. So storing word embeddings of each and every word in a sentence, and storing sentence embeddings. So S is a sentence embedding. What is sentence embedding? Suppose a sentence is composed of many words. So whatever the embedding that you get for each and every word in a sentence are averaged out. So this is the average of all the words in a particular sentence. So that will be the sentence embedding. So the similar values I have used as I have used in glove. So max length is 51 and the max features is 10,000. And I have tokenized each and every sequence, and I have also padded the sequences with respect to the maximum length, which is 51. So the embedding dimension in stacked embeddings is 6144. In the glove word embeddings, the dimension was 200 that I have used, but the stacked embeddings embedding dimension is 6144. This will vary with respect to the kind of embeddings that we consider, because here the stacked embeddings I have considered BERT as well as ELMO. Together, BERT and ELMO embeddings will be getting the embedding dimension as 6144. So I have constructed the embedding matrix, and I have created an embedding layer of the vocabulary size and embedding dimensions, and the embedding matrix as a weights. So a similar architecture I have used as I have used for glove. So here you can see the number of parameters that you are getting, because in glove it was only 200 dimensions. The number of parameters that you are getting is this number. But here, because of 6144 embeddings, you can see what is a very large number in the number of parameters. But anyways, these parameters are I have set to not trainable. Here you can see the trainable is equal to false. Therefore these parameters I have set not to train. And even here you can see total number of parameters, which is a sum of all these. And you can see the distinction in trainable parameters as well as non-trainable parameters. So the non-trainable parameters are these, which I have represented over here. So the optimizer here I have used is RMS prop and binary cross entropy as a loss function. So as I showed you in the presentation, here you can see the model has converged well with when we compare it to the glove embeddings, which is 200 dimensional. Here you can see we are getting accuracy of about 89% for the training set and 86% for the validation set, which is considered very good accuracy when compared to the static word embeddings. Yeah, here you can see the gap. Yeah, so that's it for the presentation. You can ask any questions if you have any doubts.
So, guys, any questions you have? This is a time to ask. I've already shared the CellStat YouTube link on which this webinar recording will be available in 2-3 days time. So Shreyas, you have another webinar coming up in May, right?
Yes.
So would you like to tell about it in short, in 2-3 minutes? I'll just see if any questions are coming.
Okay,
So,
for sure.
Yeah. Would averaging the word embedding result in loss of some context?
Wait, where is the question? I'm not able to see it.
No, so I'm asking you the question.
Okay.
Would averaging
Okay.
the word embeddings result in loss of some context?
Yeah, in many of the cases, we'll be losing the information. But in FLAIR embeddings, what it is being done is, let me show you this. Where is it? Okay. No. So the metric that I'm using here is the averaging. There are other metrics also in order to find out the sentence embeddings. Actually, the sentence embeddings are used like suppose if I plot a TSNE plot for my corpus that is sarcasm detection, I'll be able to easily visualize for each and every sentence. Suppose there are around 1 million words in my corpus. There will be a very large number of words which can't be visualized in a TSNE plot. That's why we'll average the embeddings for each and every word and find out the sentence embedding based on whichever metric mean. And there are also other metrics I have not explored in it. These sentence embeddings are just to visualize in a TSNE plot how it is appearing. But we are not using these sentence embeddings to train our model. Yeah, any more questions?
So yeah, more are coming. Uh, so you pass each word embedding one after another in the form of a sequence till the end of the sentence. Is that correct?
Yeah.
Okay. Any other questions, audience? I'm not seeing any other questions. You can tell about your next webinar in May.
Okay. So my next webinar in May is almost exactly 1 month from this date. So I'll be talking about interpretable named entity recognition using LIME or LE5. So the main thing here is most of the times many would have discussed how we are extracting named entity recognitions from a set of documents. But the main thing that we miss is explaining the model, how we are extracting the NERs. And suppose uh, you have got a client project, you are supposed to explain the client how you are extracting the NERs, how you are making the predictions. So to explain these deep learning models, I'm using LIME and as well as LE5 to explain how these NER predictions are being made.
Okay. So yeah, so I'm not seeing any more questions. So we would like to close it here. So thank
Okay.
you for the webinar today, and
Okay.
thank you audience for joining. And we are almost having one webinar a day these weeks, about five days a week. Look forward to see you in future webinars. Thank you, Shreyas, and have a nice day to all across the country.
Okay. Thank you, Vishal.